Hello, and welcome to the lecture on 10.9. Today we're going to talk about systems of inequalities. Instead of having a system of equalities like we have this entire chapter, we're going to modify it a little bit and use inequalities instead. But in order to do this, we need to know how to graph inequalities. Let's start here with graphing inequalities. I'm going to start by analyzing the graph y is equal to x squared. Now, we've used this graph a lot, and with good purpose. It's a pretty straightforward graph. We have this. Now, we have talked about graphing functions before and what the x value and y value are, but I'm going to go over it very quickly again. Every single point on this graph has the form x squared. I draw a vertical line here. Then x is the distance from the y-axis to this vertical line. That's what x is. In the x location, that's how far horizontally we move. And then y is the distance from the x-axis, and that's in the second location of the ordered pair. And in this case, y is equal to x squared, so we have x squared. And what this means is that this distance squared gives us this distance. This vertical distance is the square of this horizontal distance. Now, we should be aware of this already, maybe not this particular formatting of our coordinate, but we should be aware of how graphs work in general. But now this is y is equal to x squared. If we're talking about inequalities, then we're not going to have equal to, we're going to have greater than or equal to, or less than or equal to, or something where one variable is greater than or less than a function of the other variable. We make this an inequality, then the relationship between x and y changes, or our solution set. We move back up here and we look at this. Y equals x squared, the solution set is this curve. It's plotting the solution set. So every point on this curve is a solution to this equality. But if we have an inequality, say y is greater than x squared, well then this vertical distance needs to be larger than the square of this distance. Y value of the coordinate must be larger than x squared. So no longer is this point a solution to this inequality. Our y must be larger than the x squared. So again, think of our x as a distance here. So let's say that x is 3. It's clearly not because, we're on graphing paper, but let's suppose that it's 3 for a second. Then our y needs to be larger than 9. Now this graph, this point, if x is 3, then it would be 3, 9. So our y value, the solution to this inequality, must be above that. Must be up here somewhere for every single point directly above 3. Suppose we had y is less than x squared instead. Then the y value of the coordinate must be smaller than x squared. No longer larger, smaller. So it needs to be below this point in order for it to be a part of the solution set. Again, y being less than x squared, it has to be y being less than x squared means that we're not finding a solution set that's on the line, but instead below the line. I'll show you what each of these look like as a graph. Now there's 4 different versions. We could have y is strictly greater than x squared, in which case we would still sort of plot the y equals x squared, but it's not actually going to be a part of the solution set because there's no equal to here. So any point that's on this line is not a part of the solution set. So instead of making it a solid line, we make it a dotted line. And then y being greater than x squared means that we need to be above this dotted line in order to be a part of the solution set. And we can see that by plotting a point. For instance, this point here, which is 0, 2. So if we look at the point 0, 2, we can determine whether or not 0, 2 will be a part of the solution set. Plug in 0 for x and 2 for y, we get 2 is greater than 0 squared. Does this coordinate make this inequality true? If it does, then that point is going to be a part of the solution set. If it doesn't, then it's not a part of the solution set. Turns out that 2 is greater than 0 squared, so everything up here is a part of the solution set. Everything above the dotted line. Now, if instead we look at y is greater than or equal to x squared. Now the only part that's new is the equal to part. We could have y is equal to x squared now, which is exactly this curve. So instead of saying that this curve will not be a part of the solution set, it now will be because y can be equal to x squared. So again, we would plot the graph. But this time we do it in a solid line, because the equal to is a part of the inequality, therefore it's a part of the solution set. And again, we can use a test point, 0, 2. You can pick any test point, really, that's not on the line, and test it to see if the inequality does hold. And again, we get a 0 squared and 2, so it does actually hold. It means that everything above the line, including the line, is a solution set. Now notice what we did. We drew the curve in a solid line instead of a dotted line. Over here we had a dotted line. It means it's not a part of the solution set. Here we have a solid line, which means it is a part of the solution set. This is an important distinction when we go through these types of inequalities and graphing them. The next one is going to be now y is less than x squared. So notice we don't have the equal to again, which means we need to do a dotted line because y equaling x squared is not a part of the solution set. It does not satisfy the inequality. If we had a point, say 0, 0, which is on the curve, it's on the dotted line, 0 is not less than 0. So it's not a part of the solution set because it doesn't satisfy the inequality. So we draw the dotted curve, we get this. Now y is less than x squared. This means that we need to be below the dotted curve because our y values need to be smaller than the x squared value. So remember, x is the horizontal distance. The vertical distance to get to a point on this dotted line is x squared. So however far we go over, you take that distance and you square it, and that's how far you go up to get onto the dotted line. But we need to be less than that distance. Our vertical distance needs to be less than that distance. So we need to actually be below this curve. Now again, you can test a point, and we'll use 0, 2 again, and determine if this satisfies the inequality. Is 2 less than 0 squared? Is this true? No, clearly not. So this point here is actually not a part of the solution set, which means we don't shade this side of the curve, we shade the opposite side. And we get this as our solution set instead. And now the last one, as you can probably guess, is going to be y is less than or equal to x squared. And here we plot in a solid line the y equals x squared curve. Now y is less than or equal to x squared, so because we have a solid curve, it's going to be a part of the solution set, and that happens because equal to is a part of the solution set in our inequality. So if y is exactly on the curve, it's equal to x squared, which means it satisfies this inequality, therefore is a part of the solution set. Solution set being all of the points that satisfy the inequality. And then if we need to know which side of the curve we shade, we can plot a point to determine if it's a part of the solution set. Does it satisfy this inequality? Would determine whether or not it's a part of the solution set itself. So 0, 2 is here. If we plug in 0, 2, we get 2 is less than or equal to 0 squared, which is clearly not true because 2 is greater than 0 squared. We don't shade above the curve, we shade below the curve. So this is what we get. Our solution set is going to be all of these points, and it should make sense. Instead of having just the points that are on the curve, that would be equality, we have an inequality now. So either above or below the curve. And there's a lot more points above and below a curve than on the curve. So our solution sets are actually going to be much, much larger. Nope. If you are unsure which side of the curve to shade, plot a point on one side of the curve and determine if that point satisfies the inequality. If it does, then shade the side with the plotted point. If it does not, then shade the side opposite to the plotted point. Now I showed you this with each of these points here. I always use the same point, 0, 2. It's always off the curve. In the first two, it does satisfy, so we shade that side. In the second two, it doesn't satisfy, so we shade the opposite side. This technique will always work whenever you're trying to determine which side of the curve to shade for an inequality. So I recommend that you use this. I'm going to give you a guide on how to solve these types of problems when we're just trying to graph and find the solution set to an inequality. Graph the equation associated with the inequality. Note, use a dashed line for greater than or less than, and use a solid line for greater than or equal to or less than or equal to. Here, this was always the first step that we did. We graph the curve that's associated with it. You don't graph y is greater than x squared when we're trying to do this part. Graph the equation associated with the inequality. What I mean by this is, like here, we graphed y is equal to x squared. Yes, y is not actually equal to x squared in the inequality, but we still need to graph that as a boundary for our solution set, because the points start becoming a part of the solution set around the boundary y equals x squared. So here we graph the curve y is equal to x squared. And then 2, shade the solution set to the inequality. Use a test point on one side of the curve to determine which side to shade. That's what we did second. We first graphed the curve, and then we used a test point, 0, 2, in each of these cases, 0, 2, to determine whether or not this point was a part of the solution set. If it is a part of the solution set, you shade this side. If it's not, you shade the opposite side. Now this shaded, all of the points that are shaded are actually the solution set itself. So every single point here in the red is a solution to the inequality. And I can prove that to you by taking any point you want to. This point here, 1, 2, 3, -1. So -3, -1. This point, without me even needing to plug this in, I can tell you that this point will be a part of the solution set. But we plug it in to verify. You don't need to verify all the time. I might verify one point, but that would be it. Plug in -3 for x, plug in -1 for y. -1 is less than -3 squared, because -3 squared is 9, positive 9. Here we'd have -1 is less than 9. That's true. Therefore, this point is a part of the solution set because it satisfies the inequality. Now, in previous sections, we used graphing to solve inequalities, and those inequalities solution sets were only x values. Here, the difference is that our solution sets include coordinates, not just x values. They include coordinates. Now, in previous chapters, specifically in chapter 1, we talked about graphing inequalities, but they were of the form something like this, where we had maybe x squared is less than x plus 1. Now notice here that the inequality is given all in x values. There are no y values here. This would have been a chapter 1 problem. Chapter 10, these inequalities are given in x and y values. So we're no longer saying that we only want x values. We want coordinates x, y values. We're looking for all of the coordinates for which the y coordinate is greater than x squared, where x is the x coordinate. So let's do another example here. Graph the inequality. X minus 1 squared plus y plus 2 squared is less than 4. Now this problem is a bit tricky, just a bit. We need to recall a couple of things. Recall, y equals f of x minus h shifts f of x, the graph f of x, h units horizontally. Now, if h is positive, we shift to the right. If h is negative, we shift to the left. We also had that y is equal to f of x plus k shifts f of x, k units, vertically. Now notice here, we have a different sign. We have minus h and a plus k. But if k is positive, we're still shifting up, and if k is negative, we're shifting down. But for a graph like this, we can't put it into a form where we have y is equal to something. Instead, we need to look at this differently. Now remember, when I first introduced this topic way back in chapter 1, I moved the k to the left, and I had y minus k is equal to f of x. This still shifts up if k is positive and shifts down if k is negative, even though this sign is a subtraction. I haven't changed the value of this function, I've only changed the form in which we look at it. So here, y minus k shifts down if k is negative and up if k is positive. Now this is identical to this type of problem. If you remember, a circle with a center 0 is x squared plus y squared is equal to r squared. Now if I wanted to change the center of this circle, that's all I want to do is shift this circle. So I do x minus h to shift it horizontally, and I do y minus k to shift it vertically. So this would be a normal circle, centered at 0 with radius r. This circle is centered at hk, also with radius r. All we do is shift the curve, because all we're doing is affecting x directly with h units and y directly with k units. So this is what we have here. We have a circle, and the circle has a radius of 2, because remember, r squared is this side. So we take the square root to figure out what r is. So radius is 2 in this case. The center of this circle is going to be 1, negative 2, and the radius is 2. So if we graph this, 1, negative 2, this would be our center, and we have a radius of 2 units. Point. We move 2 units away from the center in all directions, and that will map out a circle. We have this circle here. Now, unfortunately, we have less than 4. So this needs to be dotted, not solid, because the edge of the circle is not a part of the solution set. Now we're saying that x minus 1 squared plus y plus 2 squared is less than 4. So we need to figure out which side to shade. I can check 0, 0 to see if this point 0, 0 is a part of the solution set or not. Does the point 0, 0 satisfy the inequality. Plug in 0 for x and 0 for y, we get a negative 1 squared plus 2 squared, and is that less than 4? 2 squared is 4, and 1 squared is 1. Is 1 plus 4 less than 4? No, it's not. So 0, 0 is not a part of the solution set. So we shade the opposite side of the curve, of the line. That will be the inside here. So the solution set to this curve is the inside of this circle that's centered at 1, negative 2 with a radius 2. Try one on the accompanying worksheet. Graph the inequality. Y is less than or equal to 2 minus x squared. The next topic I want to talk about is systems of inequalities. Definition. The solution set of a system of inequalities is the set of all points that satisfy every inequality in the system. Graph of a system of inequalities is the graph of the solutions. When we're talking about a system of inequalities, we're basically talking about 10.8 and the rest of the chapter, but having inequalities instead of equalities. We might have a system that looks something like this, where we have y is greater than or equal to, less than or equal to some function of x. Similarly, we'll have y is less than or equal to, greater than or equal to some inequality here of a g of x here. Now, when we graph these, we'll have two different functions. Maybe our f function looks like this. We draw it dotted because we have a greater than, strictly greater than. Maybe our g function looks something like this. We draw this one solid because we have less than or equal to. Now, each of these inequalities is going to have its own solution set, which has nothing to do with the other. So the solution set to this inequality has nothing to do with the solution set to this inequality. Similarly, the solution set to this inequality has nothing to do with the solution set to this inequality. Now, for the first one, we have y is greater than f of x. So if this is f of x, then we're shading above f of x here. So we would shade this side of the curve of f. Now, all of this red shading is going to be the solution set for the first inequality. Now, again, this red shading has nothing to do with this one. All of the shading that would be up here, I don't know if it satisfies this or not. What we want to do is we want to be able to find the shading for both of these inequalities, and where they overlap, those are the values that are going to be satisfying both inequalities. So here we have y is less than or equal to g of x. So we get that we shade this side of this curve. And notice that here, all of the values up here satisfy f, but do not satisfy g, because all the shading up here is only red. It doesn't have any blue shading at all. Therefore, these points do not satisfy the g inequality. All the shading down here that's only blue satisfies the second inequality, but not the first, because all of these points are not in a red shaded area. Now, this green area here is where we have shading for both. This shading is going to be the solution set for the system of inequalities because it satisfies both this inequality and this inequality because it's shaded both blue and red. All these points overlap in the solution set for both of these individually. Therefore, they are the solution set for the entire system because the solution set for the system of inequalities is a set of all points that satisfy every inequality in the system. They have to satisfy both. So it has to be where the shading overlaps. And we can extend this to have even more inequalities, 3, 4, 5 different inequalities, as long as we have shading that overlaps for all of them, we'll have a solution set. The solution of a system of inequalities. To graph the solution of a system of inequalities, we carry out the following steps. Graph each inequality. Graph each inequality in the system on the same set of axes. Graph the solution of the system. Shade the region where the graphs of all of the inequalities intersect. All of the points in this region satisfy each inequality, thus they belong to the solution of the system as a whole. 3. Find the vertices. Label the vertices of the region that you shaded in step 2. So, this follows exactly what I was talking about earlier, where if we have different inequalities, and we shade a specific side of each of these, we look for where the overlap is. This would be step 2. So step 1 would be to graph each of these and shade the side that we need to shade. Step 2 would be to look where we have overlap. Now this is the side that we actually want to shade, because this is the true solution to the system. And then step 3 refers to the points, the vertices, any sort of intersection point on the boundary. These would be the vertices of the region that we shaded. These points represent a sort of balance for our inequality. And we'll see why we label these in a little bit when we do an application problem. Example: graph the solution of the system. X squared minus y less than or equal to 4. 3x minus y greater than 0. Step 1 is to graph each of these systems on the same coordinate axes. X squared minus y being less than or equal to 4, if we solve for y, this gives us y is greater than or equal to x squared minus 4. Same inequality, add your y over, subtract your 4, we get this. Similarly, I'm just going to add my y to the other side, and I'll end up with y is less than 3x. Y equals 3x looks like this. Let's go ahead and shade a side for this line. This curve here. Label it with red. Y is less than 3x. So if I plot the point 1, 0, I can see whether or not I shade this side of the line. Plugging in 1 for x, 0 for y, I get 3 is greater than 0, which is true, which means I shade this side of the line. This is the solution set for the y is less than 3x inequality. Now I'm going to graph this curve and then graph the solution set for it individually. So we've graphed this one individually. Now I want to graph the solution set for this inequality individually. And it will look like this. 1, 2, 4. It is x squared minus 4, so we drop down 4 units. It's just the y equals x squared graph shifted down 4 units. Get something that looks like this. We graph the solution set for the parabola now. We have y is greater than or equal to x squared minus 4, so we have a solid curve. And if we plug in 0, 0, we get that 0 is greater than or equal to -4. So we shade the side with the 0, 0 point. Be this side. And then wherever we overlap, that's going to be the solution to the system. So right here. Notice up here, this is only blue. Down here, this is only red. Our actual solution to the system is all of this. And we'll get another intersection point up here. We have an intersection point right here. That one's obvious. But to find the intersection points, what we want to do is we want to set this function to this function, because these are the boundaries. Y equals, notice that we have y is equal to x squared minus 4, is the boundary for this inequality. And similarly, we have y is equal to 3x as the boundary for our second inequality. We're looking for where these two equations intersect because we're looking for where the boundaries intersect. So we set x squared minus 4 equal to 3x, and then we'll find the corresponding y values after. So we're looking for where y is equal to 3x intersects with y is equal to x squared minus 4. So we get 3x is equal to x squared minus 4. Subtract my 3x, I get 0 is equal to x squared minus 3x minus 4. Negative 4 and positive 1. X minus 4 times x plus 1 are the factors of this quadratic, which means that x is equal to 4 and x is equal to negative 1 are the x values for which we have an intersection point. Notice that this point occurs at x is equal to negative 1. The other one will occur at x is equal to 4, which will be up here. Now we need to find the corresponding y values. And you can plug these into either of these equations to get the corresponding y value. Y is equal to 3 times 4, 12. And y is equal to 3 times negative 1, which is equal to negative 3. So this point should be negative 1, negative 3, because if x is equal to negative 1, y is equal to negative 3. And then the point over here should be 4, 12. If x is equal to 4, then y is equal to 12. So we label this vertex, which is going to be negative 1, negative 3. And then our point over here, go up to this point. Shading. And this point is 4, 12. So the solution set is all of this green area. All these points satisfy both of these inequalities because they make them both true. That's the whole idea with inequalities. Try one on the accompanying worksheet. Graph the solution of the system. X squared plus y squared is less than or equal to 4, and x plus y is greater than 2. Next topic I want to talk about is systems of linear inequalities. Systems of linear inequalities is basically just a system of inequalities, but with specifically linear equations. So our system will only have lines in it. Everything else is the same. Go ahead and do an example here. Graph the solution to the system. 2x minus 3y is greater than or equal to 1, and x plus y is strictly less than 1. Okay, so let's solve for y in each equation. We'll call this equation 1, this equation 2. Equation 1, add the 3y over, subtract the 1. So we have 2x minus 1 is greater than or equal to 3y. If we divide both sides by 3, then we have y is less than or equal to 2/3 x minus 1/3, where I just reverse the inequality. Because if we divide, we would have y is less than, or 2/3 x minus 1/3 is greater than or equal to y. It means the same thing. Equation 2, if we subtract the x over, then we just have y is strictly less than 1 minus x. So let's go ahead and plot a couple of points on this line so that we can see what we get. If we plug in 2 for x, then we would get 4/3 minus 1/3, which is 3/3. So it would be 2, 1. And then rise over run would say we go up 2 over 3. So this is what this line is going to look like. Now I just need to see which side I shade. Y is less than or equal to this line means that we shade below. Now you can test a point if you want to. You can see that we actually don't intersect the point 0, 0, so we can use that as a point. Plug in 0 for x, 0 for y, and we have 0 is less than or equal to negative 1/3, which is not true. Negative 1/3 is less than 0, not the other way around. So we would shade the side opposite to the origin. The origin is above the line, so we shade below the line. Now for the second inequality, we have y is less than 1 minus x. So we graph this line as well. This one will be dotted. Now we shade the side that we need to shade. Y is less than 1 minus x, so we're going to shade below. But if you want to check, you can plug in 0, 0 again. You have 0 for x, 0 for y would be 0 is less than 1, which is true. So we shade the side with the origin. We shade this side here. Now notice where we overlap twice. We overlap twice in this region. So this is actually the solution to the system right here. We just need to figure out what this point is. If we set them equal to each other, we can find that. So this one, so this line is y is equal to 2/3 x minus 1/3. This line is y is equal to 1 minus x. So if we set these two equations equal to each other, we can find their intersection point, which will be the point that we're looking for, the vertex. We have 1 minus x is equal to 2/3 x minus 1/3. Add the 1/3, add the x, and we would have 4/3 is equal to 5/3 x. Divide by 5/3, and we get x is equal to 4/5. It's actually an ugly problem. Because this point, the point we're looking for, is on both equations, I can plug it into either of these equations. I'm going to plug it into this one because it's easier, and I get y is equal to 1/5. This point, vertex, is 4/5, 1/5. But the rest of this is the shaded the rest of the shaded region is the graph of the solution to the system. Try one on the accompanying worksheet. Graph the solution to the system. X plus y is strictly less than 2, and 2x minus y is strictly greater than 1. Be careful here. We have strictly less than and strictly greater than, so you need to make sure that you graph the lines accordingly. Do another example. Graph the solution to the system. X is greater than or equal to 0, y is greater than or equal to 0, and x plus y is strictly less than 2. Now this is what you'll see a lot in application, where you have this x and y being greater than or equal to 0. It sort of stands for the amount of resources that we have. You don't have negative resources. You have positive resources or 0 resources. So we get these a lot. X equals 0 is the y-axis. So if we have equation 1 and equation 2, we're going to graph the y and x axis respectively. For equation 1, we'll graph that in red. This is the y-axis, and the solution is greater than or equal to 0. So all x's that are to the right of the y-axis will be within our solution. Y equals 0 is the x-axis, so we shade above the x-axis because y is greater than or equal to 0. And then we need to graph this third inequality. X plus y is less than 2. If we solve for y, we have y is less than 2 minus x. That will be, it's dotted because we have strictly less than. We have a dotted line here. And I'm going to graph this one in green. We are less than 2 minus x, so we're going to graph below this line. Again, you can always check with a point. Plug in 0, 0 for x and y. That would be the origin, this point here, to see if this point is within the solution set for this inequality. Plug in 0, 0, we get 0 is less than 2. That's true, so we shade the side with the point 0, 0. Now we look for the region that includes all three colors, and that would be this little triangle right here. We have blue, green, and red all overlapping in this triangle, so this is actually the solution set here. We have the point here, which is 2, 0, 2, 0. This point here is 0, 2. This point, of course, is the origin, 0, 0. Definition. A region in a plane is called bounded if it can be enclosed in a sufficiently large circle. The region is called unbounded if it is not bounded. So basically, if it doesn't fit the definition of bounded, then it's called unbounded. Now, when we say sufficiently large circle, what we're saying is if we can enclose a region in a circle at all, then it's going to be bounded. If we can't, if there is no such circle that can contain the entire region, then it's unbounded. So this example up here is an example of a bounded region because I can create a circle, and within this circle, it contains the entire region, the black region specifically. I could even make that circle smaller if I wanted to. We only need a circle roughly this big. It can even be smaller. As long as it contains the entire region, this region is called bounded. Example. If we have a region that looks like this region is bounded because I can enclose it in a circle. When I say sufficiently large, again, all I mean is that if we can create a circle that is large enough to contain a region, then it is bounded. So this region is bounded. Now we've graphed other regions that are unbounded as well. Suppose that we have this region here. Now this region is infinite. I can create a circle that encloses this part, but you have to remember that this shading goes forever. So no matter how big the circle is, it will never contain the entire region. Therefore, it's called unbounded. We're going to do one more example, but it's going to be an application problem. Unfortunately, I'm sad to say, for the last application problem of the semester, we need to move away from Star Wars. Yeah, like y'all believe that. The factory on Lothal is set to start production of the TIE Fighters and TIE Defenders. The factory can be operational 74 hours per week for molding and 22 hours per week for assembly. They estimate it will take 6 hours to mold the parts for a TIE Fighter and 10 hours to mold the parts for a TIE Defender. Furthermore, it takes 3 hours to assemble a TIE Fighter and 2 hours to assemble a TIE Defender. Find a system of inequalities that describes all possible combinations of TIE Fighter and TIE Defenders that can be made weekly. Graph the solution. Right, there's a lot here. Let's start with a few points, and then we'll get into graphing and such on the next page. So say that X is the number of TIE Fighters that can be made. and y is the number of tie defenders. This is the number of each ship that can be made weekly on Lothal in the factory. Now I want to make a note here. We can't make a negative TIE defender and we can't make a negative TIE fighter. So we know already that x is going to be greater than or equal to 0 and y is greater than or equal to 0. This is generally understood, but a lot of times students sort of omit it. So you don't want to omit this. Now we know for the TIE fighter and the TIE defender how much time it takes to mold and assemble each of these ships. So the TIE fighter, for molding, it takes 6 hours and 3 hours of assembly. TIE defender, it takes 10 hours to mold the parts and 2 hours of assembly. So each equation is going to be related to the time it takes to mold and assemble a TIE fighter and mold and assemble a TIE defender, because we know how much time we have. We have 74 hours per week for molding and 22 hours per week for assembly. So the total amount of hours that we have is 74 per week for molding and 22 per week for assembly. So our equations are going to be related to the time it takes to mold the parts for each of these ships and the time it takes to assemble the parts for each of these ships. So we have 6 times x, because that's the number of TIE fighters that we have, and each TIE fighter, it'll take 6 hours to mold the parts for it. So 6x plus 10y, and y is the number of TIE defenders that we're making weekly, and it takes 10 hours to mold a TIE defender, so 10 times y is going to be the amount of hours that we use per week to mold the parts for the TIE defenders. And this has to be less than or equal to 74. Now, we can use less than 74 hours, but we cannot use more than 74 hours. So this will be the inequality that is a result of the amount of time it takes to mold each part for the ships. This inequality will be the amount of time we can spend molding for each ship and the total amount of time we have to mold parts for each ship. Same thing for assembly. And we have 3x because it takes 3 hours to assemble a TIE fighter, plus 2y because it takes 2 hours to assemble a TIE defender, and that has to be less than or equal to 22. Because again, we can use less than 22 hours, but we cannot use more than 22 hours. So this is our system of inequalities, including these two as well. So we have 6x plus 10y less than or equal to 74. 3x plus 2y is less than or equal to 22. We have x is greater than or equal to 0, and y is greater than or equal to 0. So what we need to do now is graph these lines. X being greater than or equal to 0 means we are to the right of the y-axis. Y being greater than or equal to 0 means we're above the x-axis. We have this so far. Next, we need to plot these two lines. Specifically, 6x plus 10y is equal to 74. I need to plot this equation, not inequality, this equation, and then we'll graph the solution set to the inequality after. I can divide everything by 2, so we have then 3x plus 5y is equal to 37. If I plug in 0 for x, I get a little bit more than 7 for y. If I plug in 0 for y, then I'm plotting on the x-axis. I will have a little bit more than 12. It'll be 12 and 1/3. here. So this is this line. 3x plus 5y is equal to 37. And then we shade one side or the other. Now we have to be less than or equal to 74. So this inequality will correspond to 3x plus 5y is less than or equal to 37 when we divide everything by 2. Now if I plug in 0 is 0 for x and y, I have 0 is less than or equal to 74. So I can definitely shade this side because I'm shading the side with the point 0, 0. So currently this is what we have. I also need to plot the solution set for this inequality. That is 3x plus 2y is equal to 22. I'm plotting this line. If I plug in 0 for x, that means I'm on the y-axis. Y is equal to 11. And if I plug in 0 for y, then I'm on the x-axis. And then I get x is 7 1/3, about here. So this line is 3x plus 2y is equal to 22. We are going to shade one side of this inequality now. Now, 3x plus 2y being less than 22 means we're going to shade below. But if you're unsure, you plug in a point that's not on the line. We can plug in the origin. 0 plus 0 is less than 22, so we shade the side with the origin. We shade this side. So we actually get this region right here, ending on this boundary, and then ending on this boundary. This region right here is the solution set. Notice, we end on the boundary 3x plus 2y is equal to 22 on this side, and then we end on the boundary up here, 3x plus 5y is equal to 37. We're going to solve the system of equations in order to get this point right here. This point ends up being 4, 5. If you just subtract the two equations, then you get 3y is equal to 15, y is equal to 5. Plug that into either, and you'll have x is equal to 4. Basically, you solve the system of equations for this. This would have been a 10.3, 10.4 problem, somewhere around there. Okay, so let's talk about this a little bit more. We can plot for any point that's in here. It would satisfy these two inequalities. That means that we can build that many TIE defenders and TIE fighters, depending on what our y and x are. Now remember, we defined x to be the number of TIE fighters and y to be the number of TIE defenders. So if I have, say, a point here at 3, 2, this point satisfies these inequalities, all of them. So I can make 3 TIE fighters and 2 TIE defenders. This is my x, this is my y, so it's 3 TIE fighters and 2 TIE defenders. This is a possibility. Now, is it the best possibility? Absolutely not. Obviously. We don't use the resources that we have. We have up to 74 hours for molding, and we have up to 22 hours for assembly. Now, the best solution would be this 4, 5. This would mean we mold and assemble 4 TIE fighters and mold and assemble 5 TIE defenders. Because remember, X is TIE fighters, Y is TIE defenders. So we can make 4 TIE fighters and 5 TIE defenders. And that will use all of the resources that we have. And we can even check that if you want to. Plug in 4 for X and 5 for Y. 5 for Y would be 50, 4 for X, 4 times 6 is 24. So 24 plus 50 is 74. And then 4 for X and 5 for Y. 4 times 3 is 12, plus 10 gives me 22. So it would use all of the resources that we have. So this is the best solution. And generally that's the case. This is why we plot our vertices, because the best solution is usually a vertex somewhere. All right, that's going to be it for today and this class. I hope to see you all in the next class. Otherwise, I hope you had fun learning math and a little bit about Star Wars.